Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at finding the volume using the washer method. In the previous two videos we looked at how we could find the volume of a solid that's formed by taking an area bounded by one of the axes and rotating around that axis. We're going to take a look now at taking any area, whether it's bounded by the axes or not, and rotating that around one of the axes. And we're going to talk about how we find the volume in that case. If we take a look at this drawing, the top function I'm going to call f of x, the bottom function I'm going to call g of x. And if I was interested in taking the area bounded by those two curves and x equals a and x equals b, and rotating that around the x-axis, so it would sort of end up being some kind of hollow shape. It would be a strange shape outside, and it would be a strange shape hollowed out. But imagine this rotating around this axis, it would create a solid. And if I were to envision that solid, I'm just going to take one sliver of this area, so it's my representative rectangle, and I'm going to rotate that around. So here's my x-axis, here's my representative rectangle, and I'm going to rotate that around the axis. Hopefully when you envision that, you can see that what's formed is a washer. That little sliver of a rectangle, which is in here, rotates around and it forms a washer. Let's talk about how we describe the volume of a washer before we talk about how we find this volume. What I've drawn here is the top side of that washer, remembering that it does have a thickness or a height. The inside radius is small r, the outside radius is capital R. So in order to describe this volume, I can take the volume of the outside cylinder, so that will be pi times r squared times the height, minus the volume of that part that's missing would be pi times small r squared times height. Now what I could do here is factor out pi, and I could also factor out h, but I'm going to do that at the back. So I could express that volume as pi times large R squared minus inner R squared times h. We're going to use that to determine the volume of that washer that's formed when we take that representative rectangle and rotate it around the x-axis. And then we're going to sum all of those slivers from A to B using integration. So let's take a look. Therefore, in order to calculate the volume of this region, if it's rotated around the x-axis, I'm going to put pi outside the integral sign because it's a constant. I'm summing all of those rectangles from A to B, and I do that through integration. So the integral of r squared, so here's the center of that washer that's being formed. So how do we describe the outside radius? The outside radius is f of x. That's the outside radius of the washer that's formed. So it will be f of x squared minus, now how do we describe the inside radius, or the radius of the hole that's formed? Well, that will be g of x. So we square g of x and then we multiply by the height of that washer, which will be the thickness of this rectangle, or the width of this rectangle, which we've discussed before is dx. So this is the formula that we will use to find the volume of a solid that's formed by taking an area enclosed by these functions and these values and rotating it about the x-axis. The important thing to remember is f of x is like the outside radius of the washer that's formed, and g of x will be the inside. So if our function is above the x-axis, then f of x will be the top curve and g of x will be the bottom curve. But if your area is below the x-axis, then f of x will be the bottom one, because it's the one furthest away from the x-axis. Let's take a look at some examples. Question asks us to find the volume of the solid of revolution generated by revolving the area bounded by y equals x squared and y equals 4x around the x-axis. So always pay attention to where the area is revolving around. The volume will be different if it's rotated around the y-axis or the x-axis. So it's very important to pay attention to where it's revolving. First thing we're going to do is draw them. So y equals x squared is one of our basic curves. And then y equals 4x, it's a straight line whose y-intercept is the origin. So we get with a slope of positive 4. So here's the region bounded by those two curves. Before we start setting up our integral, we need to know our points of intersection. We can see that one point of intersection will be 0. We need to know this point of intersection. So in order to do that, we make the two curves equal to each other, the two y values equal to each other. So x squared is equal to 4x. It's a quadratic equation. We move the 4x over, so we make this equation equal to 0. We can solve by factoring. So my two solutions are when x equals 0 and when x minus 4 is equal to 0, in which case x equals 4. So those will give us the limits on our integral. So my representative rectangle in this curve is described, my top curve in this case is y equals 4x. That's the curve or the function that's furthest away from the x-axis. And then y equals x squared is the bottom curve. That's the function that's closest to the x-axis. So now we'll set up our integral. Plugging into the formula, or just remembering what the volume of a washer is, we will get the volume, in this case, equal to pi times integral from 0 to 4 of the outside function, which is 4x squared, minus the inside function, the function's closest to the x-axis, will be x squared squared, times the thickness or the height of the cylinder or the washer, which would be dx. Let's simplify this before we integrate. So 4x squared will be 16x squared, minus x squared squared will be x to the 4th. And now we can integrate, so that will be 16 thirds x cubed minus 1/5 x to the 5th. And now we can evaluate. We put a 4 in for x, and then we put a 0 in for x, and subtract when x is 0, that value is 0. When we simplify this fraction, we get 1024 over 3. When I simplify this fraction, I get 1024 over 5. Get a common denominator of 15, so I multiply numerator and denominator by 5. I multiply numerator and denominator by 3. Subtract, and I get 2048 times pi over 15 cubic units. Now, because our fraction is getting so large, you might want to express that just as a decimal value, 428.9 cubic units. Let's try another example. In our next example, it says a bead is in the shape of a sphere with a hole drilled through the center. If the sphere has a radius of 0.64 centimeters and the hole has a radius of 0.18 centimeters, how much plastic will be needed to make one bead? We're not given any functions. We're not asked to find the area bounded by certain curves. So this is the type of question you might see that makes it much more challenging. But we do know how we can describe a sphere. We did it in the last video in terms of a function. So let's start with a drawing. If we were to take a half of a circle or a semicircle and rotate it around the x-axis, that would create a sphere. We know that the relationship for the whole circle will be x squared plus y squared equals radius squared. Therefore, y could be isolated and described as the positive and negative square root of r squared minus x squared. So the positive square root would be the top half, the negative square root would be the bottom half. So in this particular example, we could say that y would be equal to the positive square root of r squared. R is 0.64 minus x squared. We're not taking this whole semicircle and rotating it because then it would just be a sphere without that hole in the middle. So what we're going to do is take a line, because the radius of the hole is 0.18 centimeters. If we were to take a line, y equals 0.18, and take the area bounded by that line and the semicircle. If we were then to take this area and rotate it around our x-axis, we would get the bead with that center hole. So this is what we're going to do to set up our equation for volume. So a question like this is very challenging, but it might be one that you see, and I just want to show you how you would approach it and be able to do it with integrals. So our representative rectangle would look like that. Before we can set up our integral, we need to know these x values. So we know the y value at those points, but we need the x values. So we'll plug that y value in to our function. X squared plus y squared equals radius squared. And solve for x. So we're going to get positive and negative 0.61. Now we can set up our integral. So the volume will be equal to pi times the integral from negative 0.61 to positive 0.61 of the top function, or the function furthest away from the x-axis, which is this, squared, minus the function that's closest to the x-axis, or the bottom curve in this case, 0.18 squared, dx. Let's simplify and then integrate. That will be 0.64 squared minus x squared minus 0.18 squared. I can still simplify this function by squaring this and subtracting. To get 0.3772. And now we are going to integrate. So it would be 0.3772x minus 1/3 x cubed. Now I want to evaluate this function at 0.61. I evaluate it at negative 0.61 and subtract. And when I do that, I get a value of approximately 0.97 cubic centimeters. So this is certainly a more challenging question than one where you're actually given the functions, but if you do encounter something like this, now you've got an example to refer to. In the next video, I want to talk about how we find volumes when certain areas are rotated around the y-axis. So practice these first, and when you're ready, we'll take a look at the next video.